Welcome to 3.3 partial derivatives. We are now in the heart of the Calculus 3 course. Partial derivatives will be the first thing that you learn that is pretty much the same thing as the single variable type, but it's a little bit different because we have to deal with multiple variables in this chapter. So this is how the partial derivative is written. It can also be written as this right here, f sub x, like that. But we're gonna call this this is actually called I think it's a smaller delta, so it's still delta f delta x, but it's a smaller delta, and it's kind of a backward 6, so it's like a lowercase, right? This is a lowercase delta, and then the capital delta is, I think it's like that, but I'm not sure. So I'm not even sure if I actually have that on film. So the lowercase delta is like that, the capital delta is like that. I think that's, or no, the capital delta is like this. I'm sorry, that's the capital delta, the other one's the lowercase. Okay, anyways, this is how you find a partial derivative. This is a limit definition. We'll do one of them using the limit definition, but I don't really want to do this using the limit definition for every single thing because there's a very easy method you can also partially differentiate. But let's start off with the limit definition. We will have the limit as delta x approaches 0 of, so first of all, actually, probably should put f sub x is equal to limit as delta x approaches 0 of 3 times x plus delta x squared plus 2 times x plus delta x times, or 2y times x plus delta x minus y to the fourth minus 3x squared, or plus 2xy minus y to the fourth. I'm sorry if my parents are very loud, but right now we're just going to have to deal with that for now. So limit as this all over delta x approaches as delta x approaches 0. So what does that become? Well, the y to the fourth actually cancel out, if you can see, and then this becomes 2xy plus 2 delta xy. So 2xy cancels out as well, 2xy and 2xy right here. So what you're left with is 3 times x plus delta x squared plus 2 times delta xy minus 3x squared. And in fact, 3x squared also cancels out, but we gotta do the foiling before we confuse ourselves a lot more. And don't forget the limit at the beginning, or else it's not the correct expression. So first of all, let's close this down a little bit so that we have space to write for the rest of the thing. The active inspired dashboard just got, the icons got way bigger and it's so annoying now, but I'm just going to have to deal with it, so we'll deal with it. So that is that, right? Which means, what will you get? Well, you will get 3x squared plus 6x delta x plus 3 delta x squared, right, minus 2 delta xy minus 3x squared over delta x. And this is the limit as delta x approaches 0 of all of this. 3x squared minus 3x squared cancels out, and the delta x you can take off from every single term, the remaining terms. So this will be what? This will be 6x plus 3 delta x minus 2. Or no, I'm sorry, not minus 2. Minus 2. Wait, why is it minus 2? It's plus 2. I'm sorry, plus 2 delta x y. And don't forget the limit. So limit as delta x approaches 0 of this, which means this is equal to, if you plug in 0 for delta x, or I'm sorry, the delta x doesn't exist here because it's cancelled, so 2y. If you plug 0 in for delta x, you'll get 6x plus 2y. And that is your derivative. So f sub x is 6x plus 2y. So if you notice, if you just a little bit of a closer eye and notice, the y is actually a constant in this expression. So the derivative of y to the fourth, which is the derivative of a constant in this case, because it's not with respect to y, but it's with respect to x, the y to the fourth just disappears. So it doesn't, right? The y to the fourth is treated as a constant. The derivative of constant is 0, so it disappears. 3x squared is differentiated normally. 3x squared, derivative of that is 6x, and 2xy, y is treated as a constant. So what's the derivative of 2x is 2, and multiply that by y is 2y. So 6x plus 2y. So that's how we are going to be calculating the, oh gosh, that's how we're going to be calculating the derivatives. So if you were to if I were to ask what is f sub y in this case, what is the partial derivative with respect to y, and I'm just going to write this out as well, just to make you more familiar with the notation. It will be, what's the derivative of 2xy? Now 2x is all number, in like we treat 2x as all number in this case because it's a constant when we differentiate with respect to y. So that would just be 2x, and then minus y to the fourth differentiated normally, y 4y to the third power. So that's how you take the partial derivative. Okay, so what does the partial derivative represent? So the partial derivative represents the tangent line of a slice of the 3D graph at a particular plane. And in this case, with respect to x is y equals b, and with respect to y is x equals a. It's a little bit weird. Why is it different? Why is it x at y equals b and y at x equals a? It's a little bit weird, right? And the reason is we want to move on the x direction. We want to keep y constant, and we want to move in the x direction, right? We want to move across this plane, like from here to, I'm sorry, my parents are very noisy, but we can move in this direction. As we move in this positive direction, as we move in this direction right here, how is it going to change, right? We're moving in the direction where the partial derivative is with respect to, right? So in this picture, we're moving in the x direction because the partial derivative with respect to x, so we have to move in the plane of a y equals something, because we're not moving in y, right? If we're at a plane y equals something, that y is equal to that, and that is a constant. That's not moving at all. But as we move across, or as we take the limit, I guess you could say, if we move back to here, as we take the limit, as this moves closer and closer, we're only moving on this plane y equals b. We're not moving from any other direction, right? So we're moving in the x direction only. This one only in the y direction. That's what the partial derivative represents. So let's do the calculations right now. We don't need to put a tangent line, but we're going to do it, I think, in the next slide. So what is f sub x and f sub y? You guys should do it by yourself. And if you get it right, if you evaluate it at 1, 1, you should get f sub x at 1, negative 1 is equal to 2, and f sub y at 1, negative 1 is equal to negative 2, right? And what is x, y, z? X, y, z at 1, negative 1. So we got our x and our y, so we can find f of x, y is 1, negative 1, 1. Right, so that represents the point right here. So there's 1, right, 1, and then negative 1, and then, oh, I'm sorry, that's a little bit out. 1, negative 1, 1. There you go. So that's your point, and then 1, negative 1, 1. There you go. That's your point. So yeah, we just have the plane y equals b, and then the plane x equals a right here. Or in this case, it's y equals negative 1 and x equals 1, right? Those two planes you can see, and you can see that as we move across the x right here, our f sub x is 2 on this point. So as we move across the x, the slope is up, right? The slope is up right there. The slope is up on the positive x plane. If we have an xz plane right here, x and z, you would see that this is a parabola, right? Is a parabola, and the point is at x comma z 1 comma 1, and at 1 comma 1 it is on a positive trajectory right here. So that is the partial derivative with respect to x, right? Now what about with respect to y? With respect to y, it's negative. So as you can see, here's the, in fact, I don't really even need to draw a 2D representation for this. It's just y and z right here. You can kind of see that this is a part of a yz plane, and then if you have this moving down as y becomes more positive, then the rate of change with respect to y is negative. So this is negative and this is positive, and it's consistent with our result. F sub x is 2x if you haven't already done it, and f sub y is 2y. If you plug the points in, you will get 2 and negative 2. So yeah, I have already told you the ways to compute partial derivatives, and I want you to try these 3 ways to compute partial derivatives, and we will come back later. We will come back in 5, 4, 3, 2, 1. Okay. Have you tried to compute the partial derivatives? Let's see if you got it right. So the first one is take f sub x of the first one. So that would just be 25 25x natural log of secant of y. So every single, so this and this is just a constant, right? Even though it's a function, it manipulates a lot of things. It doesn't manipulate x, so it's just a constant, right? So we can take all of that out. So it actually becomes 25 times the natural log of the secant of y times x. So the derivative is just 25 times the natural log of the secant of y. 25 times the natural log of the secant of y is the correct answer. So what about with fy? So f sub y is a little bit harder because 25x is the only constant in this case, because everything else is manipulating y. So the natural log is manipulating the secant, which is manipulating y. So 25x is what? 25x is the constant, so 25x comes outside, and then we can use the chain rule to manipulate that. So whatever is at the top will be the derivative, and the bottom will be the bottom will be secant y, because the derivative of the natural log is 1 over whatever the function inside is multiplied by the function inside. What's secant y? What is the multiple, or I'm sorry, what is secant y derivative of that with respect to y? That is secant y times tan y. So we can actually just cross that off, and that will give you 25x times the tangent of y. And that is the right answer. It's a little bit tougher, but it should not be very hard. Next, what is the derivative of e to the x arc sine y? So what is f sub x? So f sub x is, well, arc sine y is a constant, because the thing that's being manipulated is a constant. So what you get is the same thing as if you were to do e to the 4x. So the derivative of e to the 4x is 4e to the 4x, right? So you got to take arc sine y, you got to take it out. So arc sine y times e to the x arc sine y. That's the answer. What is f sub y? F sub y is, well, in this case, now we actually have to differentiate arc sine y. But, well, what do we have first of all? So, we have, this is like e to the 2 arc sine y, right? So, because the x is the constant. So, what you get is, you get 2e, or no, I'm sorry. This is like 2 arc sine, so it's x e to the x arc sine y, and then multiply by the derivative of arc sine y. What's the derivative of arc sine y? Is 1 over the square root of 1 minus y squared. And that is the f sub y right there. So this is just all try to remember what is a constant, what is not a constant, and trying to remember your derivative rules that you've learned. So the third one, if you use the quotient rule on this, then you should use the quotient rule on this, but you should not leave it like that. There's a lot simpler way to make this a lot simpler, and that's taking xy out of the top and the bottom, which will get you, well, this is xy over xy times xy minus 1 over x plus y, right? Which is just x plus y. So it's just this is actually just this right here. So it's not very hard at all. So what is f sub x? Let's use the quotient rule. So you take the low function times the derivative of the high function, and the derivative of the high function with respect to x is y, minus the high function xy minus 1 multiplied by the derivative of the low function, which is 1, divided by x plus y all squared. And that is f sub x. What about f sub y? It's pretty symmetrical, it's pretty nice. You get x plus y times x minus xy minus 1 times 1 divided by x plus y all squared again. So that is your two derivatives for this one, two derivatives for this one, and two derivatives for the top question. Find the equation of a 3D tangent line. 3D tangent line. So the tough thing about this course is that lines cannot be given by just x, y, and z values in one equation. We have to parameterize our lines into x equals, y equals, and z equals components. So that's why it's a little bit harder. So how are we going to be able to find our point that we need and our vector that we need to act as a slope for that point to go through? So how are we going to be able to do that? Well, the answer is partial derivatives. So at x equals 3, x isn't moving, right? That's the first thing that we could say. At x equals 3, x isn't moving. So the x direction will not be moving. Because the x direction is not moving, then our x function, x of t, of the line, so this is, I'm going to say line is x of t is equal to just 3. Because it's not moving on the 3 direction at all. Now what about 3 comma 5? So if we put 3 comma 5 in here, what are we going to get? What are we going to get for f of x, y, which is the, so in our z direction, what will we get? We will get 1 over 16 times the square root of 5 squared minus 3 squared, which is 16 inside. So that's 4 over 16, which is 1/4. So our z is 1/4. So that we can use that as our point. So at x of t is 3, at y it's 5 plus something t, and at z it's 1/4 plus something t. Now what we need to realize is what is going to go in these two slots. So what is the derivative? The derivative, if we come back, is the rate of change, right? It's the slope of that 3D graph at that plane. The slope of the 3D graph at the plane x equals 3 in this case. So what we have to find is f sub y, right? We have to find f sub y. And what does f sub y tell you? It's the slope. So for every change, the slope is supposed to measure, the tangent line is supposed to measure, or the slope of the tangent line is 1, every 1 change in y, you get f sub y change in z, right? Every 1 change in y will get you f sub y change in z. So if we come back to this one, in this case, every 1 change in x will get you 2 change in z. So the direction vector or the vector for our line right here is 1, 2, or 1, 0, 2, because for every one change in x, it's 2 change in z, right? So the direction vector here in the yz plane is for every x stays constant. For every one change in y, we get a negative 2 change in z, right? So that's our direction vector. That's our direction vector. That's how I'm going to be telling you the vector for the line is our direction vector, right? Because it indicates the direction. So for every one change in y, right, 5 plus 1t, we get f sub y times t change in z, right? F sub y times t. So what is f sub y? F sub y is equal to the derivative. So it's just 1 over 16 times the derivative of this, which is 2y over the square root of y squared minus x squared, right? Or 2y over the square root of 2y squared minus x squared. If you want to pause and verify that this is correct, then please do so. But I'm just gonna trust my intuition and carry on, right? Continue with the problem like this. So what will this give you? Well, we already established that when you put 3 and 5 down here, that's 64. That's 4. So 4 times 16, 64. So what you'll get is 5 over 64. So what you get for the equation of the line is r, or L of t, I could say L of t like this, is equal to 3, 5, and 1/4, and add that to 0, 1, and 5 over 64 times t. Or you could put t at the beginning as well. And that's your equation of your 3D tangent line right there. Now, what do we have next? Well, so if we already found tangent lines. Now what do we need to do? We need to find tangent planes. So in single variable calculus, we do have a tangent line. Why can't we have a tangent plane in single variable calculus? Because in single variable calculus, the xy plane is your only plane that you can really work with. There's not an extra dimension that you can go through. You can't go into the screen. You can't go outside of the screen. So you can't really make a plane, except the only plane that you could make is the xy plane, right? You can't really make a plane that will stretch on infinitely, except the xy plane, right? And if you just take like one quadrant or something, or 2 quadrants, that's not really a plane. That's more like a quarter plane or a half plane. It's not really a plane. A plane has to stretch infinitely in all directions. So, and if it doesn't, then it's not a plane. So, how are we going to find our tangent planes? We're going to also have to use our direction vectors of the tangent lines that we have to that we worked with, right? So what is that again? Well, I've told you that for f sub y, the direction vector, you can get the direction vector in the y direction by having x not change, right? X won't change, 0, 1, and then f sub y, right? So that's your direction vector of the line in the y direction, which is a particular x equals something. So let's just draw that for now. Let's use red. So it'll be something like that, that, and it would change probably like this. Oh, I'm sorry. It would change probably like this, right? So that is the change. It's going positive right here, so our tangent line will probably, or tangent plane will probably be positive in the x direction. So let's just draw this line. It's supposed to be an infinite line, but I'm just going to draw like a line right there. And as it moves positively in the y direction, you could tell that it is positive, right? So that's the y direction. That's f sub y. That's how we will find our plane in the y direction. So that will lie in the tangent plane. Why will that line lie in the tangent plane? If you think about it, the tangent plane is going to have to include the approximation, the tangent plane is going to have to include the tangent lines of every single direction that goes out of this point. So it's going to have to include this, or this direction. It's going to have to include this direction. It's going to have to include this direction. It's going to have to include every single direction. So it's going to be a little bit, so that's why our vector has to be in the tangent plane, right? Because actually, as we go from this point, we're going to move towards the direction of the tangent plane. So that's why the tangent plane has to include the partial derivative direction vector with respect to y. It also has to include one with respect to x. So as y stays constant and x changes, and I will denote this with a different color, blue. So as y stays constant and x changes, right, and then we get a tangent plane like this, we get something like this, right? And this is a little bit smaller of a direction vector, but it's still positive, or well, not positive, negative, I mean, so because it's going down. So this is what we get for the direction vector in the x direction instead, not the y direction this time. So as we moved in the x direction, we get a negative vector, which actually is supposed to be like this. So it's like something like that, right? But I can't really draw it well because it's a little bit hard to draw in 3D. So these are your two vectors, and in fact, if you take the dot product of them, what you are supposed to get is the 0 vector, or f sub y dot f sub x, or f sub y times f sub x is supposed to be 0 at that point. I think. I'm not sure. It would only make sense for them to be 0 at that point. But I'll actually have to test that out. I'm not sure though. But whatever. What does matter is both of these planes are going to be in the tangent plane. Both of these vectors are going to be in the tangent plane. So how do we get a tangent plane if we have two vectors already in the tangent plane? What do we need for a tangent plane? We need a point, which we already have, right? The point would just be, well, x, y, z. And what else do we need? We need a normal vector. We need a vector that's normal to the two vectors already in here. So how do we find that? Well, we're going to say that this is, let's say this is y and this is x. Our normal vector is equal to x cross y. We have to cross the two vectors. So what do we get for the cross product of the two vectors? 1, 0, f sub x, and 0, 1, f sub y. We get, this is equal to negative f sub x. So I'm just doing the cross product real quick. Negative f sub y and 1. So for every one change in z, we get negative f sub x change in x and negative f sub y change in y. It's a little bit of a weird result, but we will see that this is the normal vector, and we will form our equation of the plane right now. So I'm just going to cross out all of this for now, and then this is our equation of the plane. It will be equal to, we're going to say that this point is x0, y0, z0. Right? x0, y0, z0. So what are we going to get? We will get negative f sub x times x minus x0 minus f sub y times y minus y0 plus z minus z0 is equal to 0. I'm sorry, I'm just squeezing this a little bit. Now if we move f sub x and f sub y over on the other side, what will we get? We'll get x, or z minus z0. So we move these two groups to the other side. Z minus z0 is equal to f sub x times x minus x0 plus f sub y times y minus y0. So z is equal to z0 plus f sub x, x minus x0, plus f sub y, y minus y0. And this is the equation of a plane for a partial derivative right here. You gotta find your f sub x, you gotta have a point, x0 and y0. You gotta find your f sub x, you gotta find your f sub y, and you need to know your initial z. Initial z, which is denoted as z0, and this is what you will get for your plane. You could also have it on this form. This form might be a little bit easier to write down because it's always equal to 0, but this form is the standard form, I think. This form is the form that I want you to put it into because it's a little bit, it's just nicer. It's a nicer form. Right, so that is it. That's it for tangent planes. That's not it for the lesson. We are close to the end of the lesson, but we are not there yet. So higher order derivatives. What's higher order derivatives? What's the higher order derivatives in a single variable calculus? That means you take more than one derivative. It's just simple, right? Higher order derivatives. Second order, take 2 derivatives. Third order, take 3 derivatives, etc., etc. Right? And this is your second order derivatives right here. You can take your third order derivatives, fourth order as well, but we're only going to work with second order for now. And there is a theorem, I think it's called, I don't remember what it's called. I think it's Fubini's theorem or something. No, not Fubini's theorem. There's a theorem that says that if f of xy is continuous, then f of xy is the same thing as f of yx. Right? So if we take the derivatives both ways, it will be fine. Right? It will be the same thing. I'll try to prove that with this function right here that we have, natural log of xy minus x squared. Let's first of all do f sub xx. First of all, what's f sub x and what's f sub y? So you should do this by yourself, and if you get stuck, then you can continue the video, and I will start in 5, 4, 3, 2, 1. So what you will get in this one is you will have to take the derivative of the outside, which is over xy minus x squared, keeping the inside whole, and then you take the derivative of the inside. What's the derivative of xy minus x squared? Is y minus 2x. Very simple. What about y? Same thing, xy minus x squared, and what will you get for the top? You will just get x, which is even simpler. This is just 1 over y minus x. Right, so two pretty simple derivatives to perform. Now where it doesn't get simple is f sub xx. F sub xx is going to be a little bit harder because of the complications. F sub xx is equal to low d high xy minus x squared times the derivative of the top, which is 2, or negative 2 actually, minus high d low y minus 2x times the derivative of the bottom, which is y minus x, or y minus 2x as well, I'm sorry, y minus 2x, and then divide that by y minus, or xy minus x squared all squared. That's f sub xx. What's f sub xy? Well, since f sub yx and f sub xy is the same thing if they are continuous, we can just do f sub yx, which is equal to f sub xy, because it's a lot simpler, right? And this is equal to, well, we could actually just take y minus x and make that to the negative first power, y minus x to the negative first power, and take the derivative of that, right? And I'm going to use the notation of del, so, or the notation of delta, so delta x of y minus x to the negative first power is equal to negative y minus x to the negative second power, and then multiply by the derivative of the inside with respect to x, which is negative 1. So that's just positive y minus x to the negative second power, which is equal to 1 minus y minus x, or 1 over y minus x squared. So that's f sub yx. What's f sub yy? We can do the same thing. We can do 1 over, right? So like this, 1 y minus x to the negative first power, and we take the derivative with respect to y. and we'll get minus 2 like that, the same thing, but we will get a negative 1, and it won't be cancelled. So what we'll end up getting is negative 1 to y minus x squared, like that. So that is f sub y. And that's it for today's lesson. I think it was a 40-minute one. It's pretty long, but I will post no, there's no homework, but I will see you next time for the next lesson, which is optimization. Goodbye.